Thank you for the introduction, Vilna. Now, ladies and gentlemen, as most of you may already know, the DMS principle, the separation principle, in this presentation, we will go through the basics as a recap to refresh on our DMS principle separation. When you have an ore body, there are some properties that one wants to exploit within that ore body. The first one being appearance, either density, magnetic susceptibility, electrical conductivity, surface properties, and the dense medium cyclone fits into the category where you have a density difference. And when you want to remove the wanted material from the unwanted material. In the mineral processing extraction process, we can use dense medium cyclones predominantly to remove unwanted impurities from the sellable product. We also have industrial mineral beneficiation where a dense medium cyclone can either be used as a final extraction method or as a pre-concentration method, such as our diamond application. Just as a basic description of dense medium separation, you have an ore body consisting of light and heavier material. Then you introduce that ore body to a medium that has an intermediate density, and you give it enough time to settle, and then separation takes place. The lighter particles will float on the top, then your heavier particles will sink in the bottom. Now, ladies and gentlemen, not to bore you much on the basics of the DMS principles, but the following animation is to illustrate how we think the separation process looks like inside our dense medium cyclone. I will remain silent during the video as it's playing, then continue thereafter. One of the most popular usages of dense medium cyclone in the diamond industry is the pre-concentration, as we already discussed on the previous slides. Now, this typical diamond flow sheet is to illustrate that the dense medium cyclone sits within a process and therefore affected by various factors within that process. As you can see, the dense medium cyclone on the typical diamond flow sheet. Looking at the critical factors that influence optimum diamond recovery in a DMS cyclone, we will look at the cyclone design, the ore characteristics, the medium characteristics, and move on to the plant operation. Starting with the cyclone design, in the cyclone design, there are certain ratios that are used for reference. Starting off with the cyclone diameter, the vortex finder, which is 43% of the cyclone diameter. Moving on to the spigot, which is 70% of the vortex finder, or 30% of the cyclone diameter. The inlet area is then converted to the same area of the circle. That ratio is 20% of our cyclone diameter. Still on the cyclone design, in diamond DMS, the product is to the underflow or the sinks, and the typical yield is 1 to 3% yield to the underflow or the sinks, meaning to the spigot. And looking at the vortex finder and the impact it has on our dense medium separation. When the vortex finder in the diamond industry, or rather the diamond application, is worn out, this results in fine diamonds losses to the overflow. That should be avoided when one has a worn vortex finder. The ratios that I just mentioned are from the Dutch state mine. For example, looking at the vortex finder being 43% of our cyclone diameter, which you can see, and on the spigot, which is 70% of the vortex finder. Moving on to the second factor that influence optimum diamond recovery, we will look at the ore characteristics, which is the mining location, the geology and mineralogy, which my colleagues will discuss more on. And then we have the clay contact, which has an impact on the viscosity. Then there's also an impact of fines on the ore characteristics, as well as the tonnages that are being processed in the DMS separation. The third factor influencing the optimum diamond recovery we will look at is the medium characteristics. If you have an unstable medium where medium is too coarse or has a low density, what happens in the cyclone is that water will report to the overflow, and then you'll also have water and the medium reporting to the underflow, which then causes an instability in the operation of your cyclone. And again, if you have the opposite case, if you have a too viscous medium where the density is similar in the feed and the overflow, now will the dense medium separation take place or will it not? The answer is no. The dense medium separation will not take place because there is no density difference for the particles to settle. Now what happens is that now your cyclone is just a pulp distributor. Still on the medium characteristics, we also have differentials that can be used to evaluate the cyclone efficiency. And as you can see, firstly, you'll have the feed density as shown, for example, as 2.65. Then you will have your overflow density currently as an example, 2.47. Then an underflow or the sinks density currently shown as 3.1. And have the cut density, which is measured 1/3 of the cyclone from the spigot. The differentials that we use is the feed to cut point, feed to overflow, underflow to overflow. And there are ratios that are used to determine if the medium is stable or too viscous. Now, looking at the example that we currently have on the cyclone, we have a feed density of 2.65 and then an overflow density of 2.47. And then when one does the calculation, the differential is sitting at 6.79, which is within the 3 and the 12% that is recommended. Alternatively, to an alternative of using the calculation, a graph can be used to determine whether the medium is viscous or unstable. So looking at the first scenario where you have a feed density of 2.77 and an overflow density of 2.54, you can see that the differential sits between the 3 and the 12%, which shows across the green cross to show that your medium is stable. Moving on to the second scenario where you have, for example, the feed density of 2.9 and then the overflow is sitting at 2.85, you can see that the differentials are sitting above the 12%, which is giving you an indication that your medium has high viscosity. That's how it is unstable. I beg your pardon, it is unstable. Looking at the third scenario, where you have a feed density of 3.13 and then an overflow of 2.44, you can see that the differentials are sitting below the 3%, which then gives you an indication that your medium is low in stability and is low in viscosity. Now, some of the medium characteristics that are a possible reason to the inefficiency of the separation of your dense medium cyclone could possibly be the medium quality, the medium size distribution, the medium grade that is being used in your dense medium separation, and the residual of the magnetism, as well as the magnetics, the non-magnetics that are within your medium. Looking at one of the reasons, if an incorrect grade is used in your dense medium separation, what will result is that your cyclone efficiency can be compromised, as well as your differentials are going to be affected. Now, moving on to the fourth factor that affects your dense medium separation within your diamond application, we will look at the size and screen prior to the DMS cyclone. We will also look at the drain and rinse screen, the pipe densifiers, as well as the magnetics, which my colleagues are going to indulge more on. Starting off with the first item, which is our desliming screen, there has to be enough water into the desliming screen, and the correct aperture needs to be used in your desliming screen, as well as the feed rate. The second equipment that needs to be looked at is to monitor your pressure within the DMS cyclone. Measuring your differentials could be one of the inspections that one can do on your DMS cyclone. Looking at the third equipment, which is your magnetic separator, the correct levels need to be used in your magnetic separator. The medium losses need to be minimized. The correct feed conditions have to be used into the magnetic separator. The fourth item that we will look at is the medium itself. You must ensure that the non-magnetics in your medium and then the correct density is used within your medium. And the medium PSD needs to be correctly evaluated. The fourth item within the medium, you need to ensure that you minimize the spillages of your medium. And then the fifth item to look at is your differentials, which is the stability and the viscosity of your medium. The fifth item that we will look at is the densifier. Ensure that the correct densifier is used for recovering your medium. Now moving on to the densifiers. The densifiers in the dense medium separation are used to recover the medium that was used during the dense medium separation. Starting off with the cyclone densifiers. The cyclone densifiers have a higher volumetric split to the overflow within 60 to 70%, then the remaining goes to the underflow. The cyclone densifiers have high water removal capacity, meaning that less volume is required to be processed through the cyclone densifier. However, there are higher medium losses on the cyclone densifiers, meaning that more medium is going to be sent to the dilute circuit and overflow to the magnetic separators. The cyclone densifiers are commonly used on the magnetite circuits such as coal applications. Now moving on to the pipe densifiers, the volumetric split in the pipe densifiers are less than that of the cyclone densifiers. On the pipe densifiers, we have 10 to 20% split volumetric to the other flow, then the rest goes to the underflow. On the pipe densifier, we have low water removal capacity, meaning that more medium has to be fed to the pipe densifier. However, on the pipe densifiers, we have lower medium losses, meaning less medium to the dilute circuit, which is why the pipe densifiers are commonly used on the non-coal applications, such as your diamond dense medium separation. Which then, ladies and gentlemen, brings us to the conclusion that the DMS separation in the diamond applications is not as simple as it seems, because the flow sheet, the entire value chain of the other equipment within the diamond application flow sheet do affect the dense medium cyclone separation. I thank you, ladies and gentlemen.